Okay, before we get started talking about the content of the notes, I wanted to go over a few things with you before you actually start taking the notes. So, number one, in front of you, you should have your notebook and a writing utensil, maybe a couple writing utensils so you can have different colors. Number two, you might be thinking, if you were in my biology class last year, Miss Sager, where are our fill in the blank notes? Well, you're getting older. This is another science class. I promise any other science class you have outside of that biology 1 class that I taught, you will not have fill in the blank notes. So, just trying to get you prepped and ready for all the science classes, hopefully in your future, by having you write your own notes. And note taking isn't an exclusive science skill. It is a skill that hopefully you've had experience with in other classes, and we're going to really tune it up in this class. So a good thing to remember in note taking is that these notes are for you. So I wrote this up here. These are your notes. So feel free to abbreviate as needed. In the notes, you'll see that I have abbreviated some things. If you don't like my abbreviations, go ahead and write the whole word. If there are some words that you're like, oh yeah, I definitely know what that word is, then abbreviate it. As long as you can understand the notes that you have written, I don't care how you write them. And number three, and make sure you are actually writing the notes, number one, and paying attention to what I am saying as we are reading over the notes together after you have hopefully written them. So I'll give you a few suggestions. Now, you don't have to take these suggestions, but I know what I'm doing somewhat, so they might be helpful. Personally, I would recommend before you start listening to this lecture or video, I think you should write the entire page of stuff down. That way you're not having to worry about writing and listening to me and pausing the video and going back and forth and switching different colors, whatever. It might be easier if you just write the whole thing down and then play the video, and you can listen to what I'm saying, maybe add some notes as I'm talking about what you already have written down. Just a suggestion. Do it however works best for you. Okay, so that's enough of intro talk. Hopefully you took my suggestion and you already have all this written down. So now we'll go ahead and talk about it. And I will emphasize anything that I think needs emphasis. I will add notes anywhere I think there needs to be extra notes, whatever. Just be following along and actively listening to what I'm saying. So the first set of notes here, just talk about what chemistry is. So starting up here, it says, chemistry is a physical science focused on non-living things. So if you were in biology with me, hopefully you remember that biology is the study of life. So biology is a biological science or a life science. Other life sciences include physiology, the study of the human body, zoology, botany, things like that. Those are all life sciences because they focus on living things. But in chemistry, we don't focus so much on the living parts of things. We focus on the non-living things. So chemistry is a physical science along with physics. They're both physical sciences because they focus on non-living things. And one of the perks of chemistry being a physical science is that physical science is very matter of fact. In biology, maybe for different parts of it, there could have been a lot of right answers depending on how you interpreted the problem, like many different factors because living things are complicated and life is complicated. But in chemistry, it's basically a lot of laws and things that we have experimented with over hundreds of years, so we know them as fact, and there's not really much variation from the study of chemistry. But even though it's a completely new realm of science that we're looking at, the scientific method still applies. So remember that the scientific method is a logical, organized way of dealing with a problem. And we have this logical, organized way so that anyone can really be a scientist. It doesn't just have to be scientists. If you think in this way, if you think in this order of steps to figure out the answer of a question, you can consider yourself a scientist. In everyday usage, you can use the scientific method in every day. It doesn't have to just be in my class. It doesn't just have to be in a lab where you recognize a problem, you propose possible solutions or plausible explanations, and decide on the best solution based on the available information. So the scientific method is truly just a way of thinking through a problem logically. And if I can teach you anything in any of my classes, I want you to learn to think for yourself and think logically about problems. There are definite steps for the scientific method. So first you have to define the problem. That makes sense. In order to solve the problem, you have to have a problem. And then after you figure out the problem that you want to look at, you should be doing some background research. So any experiment or problem that you're looking at, you're not going to know everything about it. That's the whole point. That's why you're doing the experiment. So in order to get enough information to come up with your hypothesis and do the experiment, you should be doing some background research and looking up more information about it since you don't know everything about it. So then after you know more about it, then you can develop the hypothesis. And the hypothesis, remember, is a statement that can be tested in if-then form. So remember, you say, if blah, 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 this happens, then da, 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 I predict this will happen. And that makes up your very well-crafted hypothesis. So once you have your hypothesis of what you're doing and what you think is going to happen, what are you going to do? You're going to actually do it. So you're going to develop the experiment and then test the hypothesis. So the main point of an experiment to test the hypothesis, you'll be collecting data. And data, remember, is separated into two kinds of data. So the first type of data is qualitative observations. So qualitative observations are descriptions using adjectives relative to the observer. So let's focus on the adjective. If you're talking about adjectives, those are things like cold, tall, green, solid. Those are all things that explain what you're seeing. And then also, when it says relative to the observer, if you're the observer and you say, oh yeah, it's kind of tall and it's only 6 feet, to me, who's 5'5", yeah, the 6 feet is tall. But if you're a person who's 6'3", you're like, man, it's not really that tall. So remember that qualitative data isn't the most reliable form because it is relative to the observer, but it's still a pretty good way of collecting data from your experiment. Another example of qualitative observations are the green crystalline solid. So let's say you're colorblind and you never knew it. Then you might not even realize that it's a green solid. So this is why we conduct experiments in pairs a lot normally, because that way you have another person to compare this data to, and they're like, no, that's definitely not green, that's blue. And then you can discuss amongst yourselves which one is colorblind. So qualitative observations are descriptions based off of things you see, basically. And quantitative observations are measurements that you'll collect that require the use of quantities and numbers and units. So this is very important in science. you will not use naked numbers. No naked numbers ever. If there's a number and it is not followed by a unit, I am going to be very upset because I won't even know what you're talking about. So, for example, if you just said, yes, there's 1.3. 1.3 what? So you must put the gram or inches or centimeters or whatever, or 27 degrees Celsius. You have to be putting the unit on your numbers, otherwise they are useless quantitative data. And there are two subdivisions of quantitative data. Quantitative data, the numbers, there can be extensive property and intensive property. Extensive properties depend on the amount of substance present. And intensive properties don't depend on the amount of substance present. We will be talking about this more later on in the notes, and I'll give you specific examples of things. But for now, just remember that they are a type of quantitative data because they deal with quantities. Now, from teaching these types of observations in the past, I realize that they are a little confusing. They kind of sound the same, look the same. A couple ways you can remember this. Quantitative require quantities or numbers. And qualitative, you just have to remember, are the opposite. They are just based off of observations. Another way to remember this is quantity has an N in it. And what starts with N? Numbers. So whichever way you need to keep it straight in your head will be very important. So let's look at this in a real life chemistry scenario. Down here, it says, from your experiment, you find a crystal and note that it is colorless and clear and has a density of 2.65 grams per cubic centimeter, a mass of 2.5 grams, and a length of 4.6 centimeters. Now, I want you to go ahead and identify which of these are qualitative and which of these are quantitative. Okay, hopefully you've had a second to think about it, or you paused the video to think about it even more, but I'll go ahead and help you out. Let's call the qualitative observations this purple color. So, let's go back down here to our example. You find a crystal. So there's the first observation, a crystal. Is a crystal a gas, liquid, or a solid? We know that crystals are solid, so boom, there's our first observation. We know that whatever we're looking at is a solid. And you note that it is colorless and clear. And has a density of 2.65 grams per cubic centimeter, mass of 2.5 grams, and a length of 4.6 centimeters. So your first 3 points up here were qualitative because they were observations using adjectives. And then quantitative using numbers were these 3 down here. Moving on to the next part of your experimental design. So you've conducted the experiment, you've collected your qualitative and quantitative data, and what are you going to do next? You're going to go on to your conclusion. And in your conclusion, you're going to analyze your observations and data, and study how it relates to the hypothesis. So if your data does not support the hypothesis, you reject the hypothesis. And remember, if you reject it, you're not a failure. That's a very harsh word. But you reject it because it didn't fit what you thought, but that's totally fine. You didn't know what you were doing when you started the experiment. That's why you're doing it. So if you reject your hypothesis, you can create a new hypothesis based on the data you already have collected and retest it. So it's not like you did all of these steps and you worked really hard on them and then you had to reject your hypothesis and you're going to quit. No, you're still going to use all of this valuable stuff you got up here to get to the answer that you want, or the answer that makes sense. And after your conclusion, what are you going to do with your data that you collected? Are you going to throw it away, keep it to yourself forever? No. In between here is where you would report your data or publish it. Okay, so I want you writing this in there, filling it in, squeezing it in there somewhere, because publishing it is a very important part of it. You share it with someone. That doesn't mean it has to be published in a journal. You could share it with a classmate or your teacher or anything like that. The internet, you know. And if you publish it, then other scientists can take what you did and hopefully recreate it exactly. And if they recreate it exactly, what happens here? The next steps after you publish it and a lot of other scientists pick it up and it's revolutionary and it's such a great experimental design and it's going to change everything. So they do it, they recreate the experiment and they get the same data, and that's good. And hundreds of scientists do this. It could be elevated to a law or a theory. So remember that these are not the same thing. A law is an explanation based on patterns in data. So remember, a law, an example of that would be the law of conservation of mass or the gravitational law, things like that. We'll deal with a lot of laws in chemistry. But if you remember back to my biology class, if you took it with me, you remember a lot of theories, hopefully. We talked about theories a lot, and theories is an explanation of events based on data. And it may be revised as new data becomes available. So a theory, we talked about the cell theory, we talked about the theory of evolution, we know about the germ theory, genetic theory, all of these theories, because they've been published by the original scientists and tested and validated so many times that we accept them as a scientific fact. And then I put this note down here, and this is another common misconception, that a theory does not change into scientific law with the accumulation of new or better evidence. They are separate explanations. So some people might think like, oh, a law is the top, the peak of scientific experimentation, which is not quite the way it is. A law and a theory are both very high up there. They're both explanations. They're both the peak of you can get. It just depends what your experiment was in, and that is whether it is classified as a law or a theory. A law is not better than a theory. A theory is not better than a law. They are both explanations based on facts that we have observed in experiments. And the next thing to talk about with the scientific method are models. Not those kind of models, scientific models. And scientific models are important in science because, especially in chemistry, a lot of the things that we are talking about are microscopic and we cannot see them with our naked eyes. So we have to use instruments to help us see them, or we develop models to help us visualize them. So models allow you to form concrete pictures of abstract concepts. So concrete pictures meaning things that you can picture in your mind of abstract concepts. And abstracts are just things that we have to visualize in our mind because we've never seen them before, because in our case they're so small. Models are also important to help communicate knowledge to others. So lots of times in science we'll use models so that you, the student, are able to learn better, or you're able to teach your peers about something that you can't actually see. Which goes along with this bullet. Explain things that can't be observed directly. In models, it's not like they just make up models and they're like, oh, I think this is what it looks like. No, they're based on some sort of data, and from that data, they figure out what makes the most sense. Models can be graphic, pictures. They can be graphs, which we will deal a lot with. They can be lengthy descriptions, or they can be physical models. So chemistry, it is a physical science, and chemistry is defined as the study of matter. And what is matter, you ask? Well, we'll get to it in a second. But it's a study of matter, matter's composition, and the changes that matter undergoes. And questions often asked by chemists: why is this matter? How much matter is there? And how can matter change? And in chemistry, we'll also look at types of experiments that are performed and what does a chemistry experiment actually look like. But hey, you already know what an experiment in chemistry looks like because you've already done one. So keep that in mind. Moving on to matter. If you want to separate this somehow, notice that this is in all caps and it's bolded. Bold? I don't know. That means we're kind of changing the topic up. We're not talking about chemistry explicitly anymore like we were all up here. We're going to be talking explicitly about matter. And matter is anything that has mass and takes up space. So if you have mass and take up space, you matter. Again, hopefully you've had this whole page written down now, including this graph. And we'll go ahead and talk about it even more. So remember from our previous page that we're talking about matter. And matter can be transformed or changed by energy. So remember, let's go down here, that matter isn't created or destroyed, it's only changed. That's a very important part of chemistry, is that matter isn't created or destroyed, it's only changed by energy. And now, what are some types of energy that it could be changed by? And I want you writing this. Types of energy could include heat energy. If you apply heat to something, it could change the matter. It could be light energy. Remember, energy from the sun. Or types of chemical energy. Those are a few types of energy that can cause this change in matter to where it is changed into something else. So remember, this idea that matter is neither created nor destroyed, that is the law of conservation of matter. Matter is always conserved. And there are different types of matters, and this graph, and this concept map sort of walks us through it, and then they're explained further down there. So matter it can either be separated or it cannot be separated. So let's focus on the types that can be separated. So if it's matter and it can be separated, then it's considered a mixture. If you mix two different things together, it's going to be a mixture. And then the next division of mixtures is the composition uniform? And we'll discuss what uniform means further below. But if it is uniform, then it's a homogeneous mixture. And remember that homo means same, so it's the same throughout. And then if it is not this, if the composition is not uniform, it is a heterogeneous mixture. And hetero, remember, means different, so it's a different composition throughout. So these are the two types of mixtures. Let's go back up, starting at matter. Can it be separated? No. If the matter cannot be separated, then it's considered a pure substance. And pure substance can be broken down even further into two different categories. Decomposed by ordinary means. Let's say no, it cannot be decomposed. Then it's an element. And an element is just the smallest thing that retains the properties of that element. So an element is just an element. Can't be decomposed. But a pure substance can be decomposed, and those are known as compounds. So we'll look at those a little more down here. Like I was saying, an element. We're going to talk plenty about elements, so this is a pretty important definition. An element is a pure substance, abbreviated like that cannot be broken down into simpler substances by chemical means. Elements are composed of only one atom, and if you need a reminder, an atom is the smallest unit of an element that retains the identity of that element. From your bio terms last year, maybe you remember that A means without and tom means cutting. So atom literally means without cutting. It can't get any smaller. It physically cannot be cut. An element is represented on the periodic table. For example, the element sulfur, the element silver, and the element erbium. Three of my favorites because they spell out my last name. And there are types of diatomic elements. Di meaning two, literally elements with two atoms. So these are things that occur as molecules of two atoms of the same element. For example, hydrogen is going to have two hydrogens. Nitrogen gas, oxygen gas, all of these gases are going to have two atoms because they're diatomic elements. So it'll be H2, N2, O2, Cl2. You get the gist. So the other type of pure substance was a compound. And compounds are pure substances formed by combining different elements into a definite ratio. For example, the compound NaCl is in a 1-to-1 ratio. A compound has properties different from the constituent elements. So alone, sodium and chlorine in separate are very reactive. They are very dangerous chemicals, but when you put them together in this compound to form NaCl, which is otherwise known as table salt, obviously table salt is not super destructive because we use it every day. Compounds can only be separated by chemical processes, not physical processes. So, for example, the electrolysis of water can separate water into 2 atoms of hydrogen and 1 atom of oxygen. But there's no There's no physical process. Like, you can't take teeny tiny little super sharp scissors and cut the water. You can't cut table salt. It's just going to be smaller pieces of table salt. It has to be a chemical process to break the bonds of whatever you're looking at, either table salt or water. Some common examples of compounds are H2O, which is water, CO2, which is carbon dioxide, NaCl, which is table salt, and C6H12O6, otherwise known as our favorite from biology, glucose. And compounds always have the same composition, which is another law. Like I said, they're super important in chemistry. That's the law of definite composition, meaning water is always going to be H2O. If it was H2O2, it would be something completely different that would kill you. Even though it's only one oxygen atom off, it forms a completely different compound. Okay, moving on to the types of mixtures. A mixture is matter that can be physically separated into its components. It has a variable composition. For example, salt water can have a little salt or it can have a lot of salt, meaning that it has different levels of salt in it, but it's still salt water. So in the same example, you could have super syrupy sweet tea, and that's the best. Or you could have some really weak sweet tea that no one wants to drink. It's still sweet tea because it has sugar in the tea, which is basically water, but you can obviously taste the difference. So the one type of mixture is a heterogeneous mixture. Heterogeneous mixtures are not evenly distributed, or they have a different distribution, if you need to remember it that way because of the prefix hetero. They can also be called suspensions. And in heterogeneous mixtures, the particles will often settle to the bottom if you leave them for long enough. Examples of heterogeneous mixtures are paint. So if you are like repainting your room or something and you buy a gallon of paint and you leave it for a really long time, you have to stir it or shake it, otherwise it will have separated into its different parts and the color won't be uniform. Many liquid medicines, so lots of medicines say like shake before you use them, and that just means to shake them so that you can get them more evenly distributed. And muddy water is another example that you might be familiar with. If you take a cup of river water, that muddy river water, and you leave it for long enough, the mud, the clay, the dirt will separate out to the bottom, and more clear water will be left at the top. So those are examples of heterogeneous mixtures because they're not evenly distributed and they're made up of two or more different things. Now, homogeneous mixtures, remember, homo means same, and homogeneous mixtures, they're also known as solutions, which I abbreviate that way. Homogeneous mixtures are composed of solvent and a solute. Remember, a solvent is the dissolving medium, or it's usually the one in greater amount. So the thing you have more of in a solution is probably going to be the solvent. So a most common example of solvent is water because it's the universal solvent, meaning that universally water is a solvent. It dissolves things. And a solute is the substance being dissolved. For example, a sodium chloride solution, a supersaturated sucrose solution, or sweet tea, or coffee. Coffee is also an example of a homogeneous mixture, because no matter how long you leave coffee or sweet tea sitting, it's not going to really separate because it's homogeneous. It's become a solution. So remember that mixtures can be separated. The separation uses techniques based on physical properties of mixture components. So what works to separate one mixture will not necessarily work to separate another mixture because they are different compounds. They're made of different things. Some common examples of separation include filtration, distillation, mechanical, magnetic, or electrostatic. But the most common two are filtration and distillation. Filtration, as the word implies, uses a filter or a barrier with small holes to separate undissolved solids from liquids. And distillation uses boiling points to separate two liquids or the solute dissolved in the solvent. For example, if you were going to evaporate the water out of salt water, leaving just the salt. Distillation can also be used to separate alcohols from water after fermentation in the production of liquors and other alcohols. And just like there are different types of matter, there are different states of matter or different ways that they exist. So the first state of matter is a solid, and solids have a definite shape and volume, and the particles are in close proximity and are held in place, which is why they can maintain that definite shape and volume. And down here, you'll notice that I included this picture of the different particles, and so I want you to draw this as best you can. For the solid, the particles, these gray things inside, they are held within the boundary for the solid. And then the other type of state are liquids. Liquids have a variable shape, meaning that the shape can change. But even though the shape changes, they will have a definite volume. A specific amount of liquid will have a specific volume, no matter what shape the container that it's in is. The particles are still in close proximity, but they slide past one another freely, which is why it can be more liquid. They're able to move more. That's what this is kind of showing, that the particles are more freely moving than the solid. But it's not like they're bouncing around. There's not a lot of free space. Most of the liquid is still within this boundary. And then the third state that you are probably most familiar with is gas. Gas, like liquid, has a variable shape, but it also has a variable volume. So depending on the container that the gas is in, that'll change the volume. And in the gases, the particles are far apart, and it's mostly empty space. So you can see over here, it's illustrating that the gases are moving a lot more. If you just want to illustrate that with a little arrow, that'd be good. This one has a big arrow. This one has a little arrow. That one doesn't have an arrow at all. But the gas, you can also see, is outside of the bounds here. So these three things down here are referred to as the particle models. So even though we can't see these particles, we know that they exist through experimentation, and this is our best way, or one of the best ways, to illustrate how they behave through these drawings that you should have drawn in some way on your notes. But solids, liquids, and gases behave differently in confined spaces. So solids, they're not going to move. They're going to stay within that confined space. Liquid, they're going to move around a little, but mainly stay within the confined space. And then gas is going to move a lot more and fill up the container. And for the longest time, these were the only three states that scientists knew about. But now we know that there exists a fourth state of matter, and we're going to write that down here underneath the particle model, and that is plasma. So I want you writing this in. If you didn't leave room down there, I don't know, make room off to the side over here. But plasma, you might be familiar with that because of plasma TVs, and they are named that way because they do the smaller cells in the TV do contain plasma. And so plasma is, the definition is a hot, ionized gas meaning in the ionized part means that it has equal numbers of positively charged ions and negatively charged ions. And in space and in the universe, there's also lots of plasma. In fact, it makes up to 99% of the universe, this plasma does. And while it does say gas, it behaves a lot differently than this type of gas, which is why they've distinguished it as a fourth type of matter. Now we're going to go over the changes of state. So these are the ways that compounds can go from solid to liquid to gas, or vice versa, or any combination of those. So we're going to go over that here. Okay, so let's just think of one of the most common compounds that you are familiar with, and that is probably going to be water. Okay, but any type of compound or substance can go through these changes of state. You're probably just most familiar with water. So let's just start off with water in the solid state. Water in the solid state we call ice, but it's still water. It's still H2O, even though it's in a solid state. So when you leave ice out for a long time and it gets heated up, you know that it goes from a solid to a liquid, and that process is called melting. So your ice melts, or whatever substance we're talking about. So going from a solid to a liquid is called melting. If we were to go, however, from a liquid to a solid, so from, say, liquid water to solid water, we'd call that freezing. So hopefully you've heard of those two. Obviously, those are the most familiar. And then if we go from a liquid to a gas, that is called boiling. So in the experiment with the boiling water, you started off with a liquid water, and if you let it boil for long enough, you would have zero water in your container because it would all exist as a gas, which we cannot see. And if gas is going from, or if water is going from a gas to a liquid, we call that condensation. And a really common example of condensation is if you have a water bottle and it's super cold, you will end up with condensation or liquid water on the outside of the water bottle because it went from a gas to a liquid. It condensed or went through the process of condensation. And then the most unfamiliar to you are probably going from a gas to a solid or going from a solid to a gas. But it does happen, maybe just more unfamiliar to you. So to go from a solid to a gas is called sublimation or to sublime. It's not just a great band. It is a scientific term. And then gas going to a solid is known as deposition, and it's much more rare than these. You've definitely heard of these ones right here, but sublimation and deposition are probably two that might be new to you. And so that brings us down here. So the changes of state, the state that it's in, either solid, liquid, or gas, is defined as a physical property. So a physical property is a characteristic of a substance that can change without, I'm going to underline that, without the substance becoming a different substance. So whatever it starts out as, that's what it will be at the end, only it's changed in some physical way. There are two types of physical properties. The first one is extensive. Extensive properties depend on the amount of matter that is present. For example, volume, mass, energy, and odor. They all depend on the amount of matter that is present. So obviously volume, however much there is going to change the volume. The mass, how much matter it's made up of, does affect the mass. The energy, so if there is more energy being applied to something, it obviously will affect it more than if there was a low energy being applied. So opposite of extensive are intensive properties. And these are properties that do not depend on the amount of matter present. And for example, these are melting and boiling points. And melting and boiling points, that's you can make a little note here, because when we did our boiling water lab, a lot of you for the question that asked about like why was our boiling point not at 100, some people may have thought, oh well, we didn't have that much water, or we had a lot of water, and so maybe that affected the boiling point. That is not so. No matter how much water you have or how little water you have, it will always start to boil at 100 degrees Celsius. However, it might take a longer period of time if it's a large amount of water, or a short amount of time if it's less water. So that does not matter on how much is present. Density also. The ability to conduct electricity. So that's just like a yes or no. Like, does it conduct electricity? Yes or no. If there's more of something, it's not like a better conductor. It's still the same conductor. And then color. Color does not depend on the amount present. And with physical properties, we have physical changes. So a physical change is a change in form, but not a change in composition. Meaning that the properties, especially chemical properties, remain the same. So if we're talking about water or H2O, it will still have 2 molecules of hydrogen and 1 molecule of oxygen bound together. That's a chemical property that will not change with a physical change. So examples of physical changes are breaking or tearing or cutting. If you mold something, the shape of it, if it's just shaped differently, if you change the shape, it's just a physical change. If it's dissolved, that is really important. Because a lot of times we think, oh, we can't see it anymore, so that means it must have gotten broken up within whatever solution it is in, but that's not often the case. So going back to my favorite example of sweet tea, even though the sweet tea even though the sugar is dissolved in the sweet tea, if through different means you could still separate it. You could separate the sugar from the tea, meaning that the sugar didn't dissolve. It's still sugar, that's why it's still sweet, because it didn't break apart into the water. And then the really big important one is change of state. So, for example, going from a liquid to a solid, or going from a gas to a solid, or a gas to a liquid. Those are all going to be physical changes. So in our boiling water lab, when it went from liquid water to water vapor, the gaseous form, it did not go from water to steam, which is something else. No, it went from liquid water, which was H2O, to gaseous water, which is still H2O. So opposite of physical properties, there are chemical properties. And that is just the ability of a substance to change into a different substance. So you'll start off with something, it'll go through a reaction, and then it'll turn into a completely different substance. Either bonds will break or form, and that will change the entire composition. So it's a chemical change. Examples of these that you might be familiar with are combustion, which is the scientific term for something burning, and then rust. Rust is a chemical change. So chemical changes or chemical reactions are just from the formation and breaking of chemical bonds. And they allow for the production of a new substance. So if we need to create a new substance or make more of a substance, we have to go through this chemical change where bonds are broken or formed. So obviously, if we're just looking at a reaction, we can't see, oh, the bonds are breaking. We can't observe that with our eyes. So some of the macro, what does macro mean? It means large. So large evidences of chemical reactions include color changes. For example, leaves turning color. So when the leaves turn, from a green to a brown or yellow or orange in the fall, that's a chemical change. Or a apple browning. So if you cut an apple in half and you're like, oh, I'll only have half of it and I'll have the other half later, and then you come back later and it's brown, that's because there was a chemical change in the air reacted with the inside of the apple that caused it to change chemically. Another example of macroscopic evidence is the formation of a gas. So if you mix two things together and a gas forms, that is normally an indicator that it was a chemical change. For example, if you put vinegar and baking soda together in a safe laboratory environment, normally it will bubble and there will be a gas that is formed. Another macroscopic evidence is the formation of a solid precipitate. And a precipitate is just anything produced from a reaction that is solid. Another macroscopic evidence is change in energy. So remember, energy comes in lots of forms, and so it can be the emission of light, like in combustion. So fires emit light because it's a chemical reaction, it's a chemical change. And also the change in heat. So again, combustions let off a lot of energy in the form of both light and heat. So when there's a change in heat, there are two types, and these are super important to understand and kind of remember, so we're going to highlight them. And the first type of heat reaction is exothermic. We're going to underline exothermic. So think about your bio terms if you had me last year. What does exo mean? Exo just means outside or release. And therm, remember, means temperature. So in an exothermic reaction, heat is released. If heat's released, that means it becomes hotter. And then there's also an endothermic reaction. And remember, endo means into or inside, and thermic, again, means heat. So an endothermic reaction is one that absorbs energy or absorbs that heat, meaning it becomes colder. So thinking about a combustion reaction, a fire, does it let off heat or does it absorb heat? It lets off heat, and that's how we can use it as a source of heat to, warm our homes or whatever. And so a combustion reaction is an example of an exothermic. And any chemical change that we talk about in here is going to be represented by a chemical equation, which hopefully you were pretty familiar with. Those chemical equations, like one we got pretty familiar with last year in biology, and that was C6H12O6 plus 6O2 yields 6CO2 plus 6H2O plus energy. And remember that the reactants are on the left side. So these are all of the reactants. And the products go on the right side. So on the reactant side, we have glucose plus 6 molecules of oxygen gas yields 6 molecules of carbon dioxide, 6 molecules of water, and that form of energy right there. And this is which biological process? In which process do we take in glucose or a carbohydrate and oxygen and release carbon dioxide, water, and energy? That reaction is cellular respiration. All right, so that does it for the first set of notes. Make sure you keep up with these because you will be adding to them.